Hello and welcome. This is going to be our lecture video on the Newton's Laws of Motion packet. It was kind of a long packet, so I'm just going to go through quickly. Think of this more as just a way for you to check your answers. Let's get started. So problem number one, which law is associated with inertia? That's the first law. If you increase the force of an object, what happens to the acceleration? It also increases. If you use the same force on a less massive object, what happens to acceleration? It would also increase. To keep the force constant, if the mass is going down, acceleration would go up. In response, which law states force is dependent on the mass and the acceleration of an object? That's the second. And what causes an object to slow down or speed up? So it is force that causes an object to slow down or speed up. Acceleration is how we describe the change in speed, but the cause is force. What law is known as the law of action-reaction? That's the third. Which law explains why when you bump into something, you fall backwards? Also the third. If you double the force on an object, what happens to the acceleration? It also doubles. In response, if you double the mass of an object, what happens to the acceleration? It is cut in half. All right, force is measured in newtons. A newton is based on basic units of the metric system. What is a newton equal to in terms of units of mass and acceleration? So 1 newton equals 1 kilogram times a meter over a second squared. So the unit for mass is kilograms, the unit for acceleration is meters per second squared. Put them together, you get kilogram meters per second squared. All right, on to the exercises. There was a lot, so I think I'm just going to skip around a little bit, and hopefully that'll be enough for you to check and see if you're doing these correctly. So questions 1 and 2 here ask you to kind of just explain some things in physics. With number 1, there's this purse that falls onto the floor. I think that's best explained by Newton's first law, that while you're driving, a purse in the passenger seat is in motion, and it's not going to stop being in motion even when the car is stopping until something physically acts on the purse, like it hitting the glove box. So that is probably how the purse ended up on the floor. Number 2 is asking about Newton's third law. And so when you're jumping off a diving board, how is that Newton's third law? Well, you push down on the diving board, and then the diving board pushes back on you. And as you launch off the diving board is pushing you up into the air, but also pushing itself down into the pool deck with an equal and opposite force. All right, number 3, you know that the mass of an object and the applied force to the object to make it move. I didn't read that right. You know the mass of an object and the force applied to the object to make it move. I did read it, it just doesn't make sense. All right, which of Newton's laws of motion will help you calculate the acceleration of the object? That's going to be his second law, because force equals mass times acceleration. Number 4, how many newtons of force are represented in the following amount? 3 kilograms times meters per second squared. Well, that's just 3 newtons, because that unit right there is a newton. All right, your shopping cart has a mass of 65 kilograms. In order to accelerate the shopping cart down an aisle at 0.3 meters per second squared, what force would you need to use or apply to the cart? Well, this one we can just directly use force equals mass times acceleration. Force equals 65 times 0.3, which equals 19.5 newtons. A small child has a wagon with a mass of 10 kilograms. They pull with a force of 2 newtons. What's the acceleration? So again, I use force equals mass times acceleration, but I know the force and I know the mass. I don't know the acceleration. So I have to divide both sides by 10 to solve for the acceleration here. 2 divided by 10 is going to be 0.2. So 0.2, the unit there is meters per second squared. All right. 3 action-reaction pairs while dribbling a basketball. So I'll just do these out loud. When you push down on the basketball pushes back up on your hand. When the basketball hits the ground, it's going to push down on the ground, and the ground is going to push back up on it. And the entire time, gravity will be at play. So gravity will be pulling down on the basketball, and the basketball will be pulling up on the earth. All right, so there you go. 3 action-reaction pairs. All right, on to page 3. So restate Newton's first law in terms of acceleration. Here's how you could do it. You can just say an object won't accelerate without a force. If the forces are balanced, what is the resulting acceleration? It should be 0. All right, we need a net force to cause acceleration. An object's resistance to change in motion is dependent solely on what quantity, that is its mass. Mass resists acceleration. Inertia is the resistance to change in motion, so inertia depends solely on what? Well, 2 things, mass and velocity. What is required to cause acceleration? An unbalanced force. What is the net force if you push a cart to the right with 5 newtons and your friend pushes it to the left with 5 newtons? It is 0. That is an example of a balanced force. And what is the net force if you start to pull instead of pushing? Then it would be 10 newtons because you get to add them together if they're pointing in the same direction. It's just vector addition at that point. And since it's a force and it's a vector, we should say, which side were we on? We were pushing to the right, so it's now we're pulling to the left, so it's 10 newtons to the left. All right, next question. So suppose you throw a rock in deep space, what's going to happen? The rock's going to travel forever at a constant velocity. Now suppose that you are also in a weightless environment. Would it require force to set an object in motion? That's just a big old yes. That's what Newton's first law says. If something is at rest, it requires a force to get moving. Why doesn't a ball roll on forever after being kicked at a soccer game? The answer to that is friction. Friction always opposes motion. It will slow anything down that is moving and is in contact with something else. All right, 2-kilogram object is moving with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed in this direction? Kind of a trick question. It's 0 newtons. To stay at a constant speed, you don't need to add any force. That's what Galileo proved. So then we got this student Ben is being chased by a moose. If Ben makes a zigzag pattern through the woods, he will be able to use the large mass of the moose to his own advantage. So yes, the moose is going to have a hard time changing its direction because that requires force. And since it has a large mass, it's going to require even more force to cause the necessary acceleration. All right, number 6, we've got Luke drops a weight off the roof of his house and into a swimming pool. Upon encountering the pool, the object encounters a 50 Newton upward resistance force. So use the description to answer the following. Which of the following velocity versus time graphs best describes the motion of the object? So I would expect the velocity to increase in a negative direction. And then once it's in the pool, perhaps the force up on it is balancing the force down, and it then takes on a constant velocity, which actually it is. 50 will balance the 50. So graph B, once the object hits the water, the forces are balanced and the object will stop. No, that's false. They're balanced, so it continues at a constant velocity. To bring it to a stop, you would actually need greater upward force than the downward force to change the velocity. So the top of this next page shows us how we can rearrange the force equals mass times acceleration formula to get acceleration equals force over mass, which is an equally valid equation. So what two variables is acceleration dependent on? Well, force and mass. The three are just inextricably linked, so force and mass. What is the relationship between these two variables and acceleration? So if we increase force, we will increase acceleration. If we increase mass, we will decrease acceleration. If an object is not accelerating, what you can determine about the sum of all forces on the object, they are zero. If the net force of an object is in a negative direction, what will be the direction of the resulting acceleration? Also negative. Yep, because the one thing we can say for sure is that the mass won't be negative, so the sign will carry across there. If you double the net force, what will happen to acceleration? It will double. If you double the mass while leaving the net force unchanged, it'll be cut in half. To answer number 6, all you have to do is just multiply those two numbers because force equals mass times acceleration, and you should have gotten 11,949 newtons of force. If we can maintain that amount of force, it will continue to accelerate until the force is lifted. It gets harder and harder to apply that force to a car that's moving faster and faster. All right, let's see how you did on this next part. So we've got a bowling ball at rest. That at rest is the giveaway that there is no net force. So 0 newtons is the answer to part A. If we push the ball with a force of 22.8 newtons, which introduces a negative 2.3 newtons of frictional force, what is the net force while you're pushing the ball? We'll just add these two numbers together. So 22.8 minus 2.3 is going to be 20.5 newtons. What is the acceleration caused? So we know force equals mass times acceleration. We'll take the force, 20.5, and divide it by the mass, 7.26. So 20.5 divided by 7.26, we should get an acceleration of 2.82 meters per second squared. All right, following your push, the ball rolls down the lane at 4.2 meters per second. What is the net force on the ball as it rolls down the lane at constant speed? Another kind of tricky question. That's another 0 newtons because it's the constant speed. How long did you push the ball in this situation? So we're going to use a kinematic to figure out how we went from an initial velocity. Oh, it's not a pen, that's my highlighter. An initial velocity of 0 to a final velocity of 4.2 meters per second with an acceleration of 2.82. And now we just have to find the time. So let's pick our kinematic that links all three of these. We're looking for the one that doesn't have distance in it. That is the one that just is V final equals V initial plus AT. So V final 4.2 equals 0 plus AT, so 2.82 times T, divide both sides by 2.82. divided by 2.82. We were in contact exerting that force for 1.49 seconds. All right, to complete the following table, we make sure to include units in your answer. So force equals mass times acceleration. So we were just going to divide here. 5 divided by 2.5 is 2. And 2, and the unit here is meters per second squared. And then as you go down, just divide each time. Do force divided by kilograms, and you'll get all of these. Number 9, here we've got different things missing, but again, just force equals mass times acceleration. So when force is missing, it's nice and easy. You just multiply these two. That'll be 16. When one of these is missing, you have to divide away. So 25 divided by 4.998 is 5.002 kilograms. Here again, we would have to divide 53 divided by 3 equals 17.67. Divide again here, 172.44 divided by 4.665 is 36.96 kilograms. And then another one where we can just multiply these. 1,225 times 3.43 is 4,201.75 newtons of force. All right, on to some more Newton's second laws. So we've got a 2,000 kilogram truck, 4,200 newtons. So force equals mass times acceleration. We'll just divide the mass away from both sides. So 4,200 divided by 2,000 kilograms gives us an acceleration of 2.1 meters per second squared. Another acceleration. So take the force, 25 divided by the mass, 0.3 kilogram. This would be 83.33 meters per second squared. So that's actually a good amount of acceleration. That's about 8 gravities worth of acceleration. How much force is needed to accelerate? So force, so we can just multiply these, mass times acceleration, 68 times 1.2. I got 81.6 newtons of force required. This next one, 30 newtons divided by that acceleration is going to give us 6 kilograms. Force on an elevator that is free falling. The free falling doesn't matter. It's still going to be experiencing the force of gravity. So multiply these, it's going to be experiencing 9,800 newtons of force. Object that needs a force of 4,500 newtons to accelerate at a rate of 5. So we'll just divide. 4,500 divided by 5 gives us a mass of 900 kilograms. All right, so finding acceleration, we'll just divide there. 12 divided by 6.4 is 1.875 meters per second squared. And then mass of an object that needs a force of 6,600 newtons to increase its speed to 107 meters per second in 2.3 seconds. So let's solve for the acceleration. Acceleration, we could do, okay, V final equals V initial plus AT. Final velocity is 107. It's starting from rest, so that's 0, plus the acceleration times 2.3 seconds Get rid of the 0 and divide both sides by 2.3. We get 107 divided by 2.3 is an acceleration of 46.5. And now we know the force, so force equals mass times acceleration. We'll take the force and divide it by the acceleration, so 6,600 divided by that number is 1,000, or no, not 1,000, 141 point, we'll round up to 9 kilograms. 141.9 kilograms will be the mass of this object. All right, so all forces result because of interactions between objects. Forces come in pairs. What are these pairs called? They're called action, reaction, force pairs. All right, and then we can label these. So we've got this guy pushing up on a bar, so the bar is going to also push down on him. Bowling ball hits a pin, so the pin is going to push back on the bowling ball. Air pushes out on a balloon, so the balloon is going to push back on the air. So these arrows are coming into the middle of that balloon. All right, so we've got a student pulling on a rope with a force gauge in between. They're pulling with 500 newtons left. All right, how much force is the wall exerting on the rope? Well, it's going to be 500 newtons to the right. What is the net force on the force gauge? So it's 500 newtons left, 500 newtons right. Its net force is 0. All right. So would the physics student be moving? No. What would happen if the wall stopped exerting a force? The student would fall over. The student, they would accelerate. Next question, what happens if the physics student is standing on ice? They can't pull as hard because they can only pull as hard as they can push the ice away from them. And if it's, slippery, they're not going to be able to push the ice as hard. Therefore, they can't get as big of reaction force from the ice and pull as hard. What is the force between the student and the ground called? I would just say gravity / normal force. We have two different forces that you could think of. We need 3 sets of force pairs in this diagram. So we can do, maybe for this guy, we'll just show gravity. Pick a spot on the rope and show tension pulling in both directions. And we also have the normal force from the ground and the force of our strong man on the ground. Notice that the normal force and gravity, they are not a pair in themselves. They each have their own pair. So that's gravity, and this is the normal force. And this over here we could call tension. All right, last page. The force pairs are drawn in the diagram on the left. What is the action force acting on? It is acting on the exhaust, or the fuel that's being ejected out of the back of the rocket. I'll just call it the exhaust. What is the reaction force acting on? It's the rocket itself. The exhaust is being pushed down so that the rocket gets a reaction force to go back up. If the forces are equal and opposite, why does the rocket ship move? It's well because they act on different things. So they're equal and opposite, meaning the exhaust gets pushed down with the exact same momentum as the rocket ship goes up. So they act on different things. All right. In fact, action reaction forces never act on the same object. It's always two separate objects. All right. Manuel's holding a 5-kilogram box. How much force is the box exerting on him? Well, we can just mass times acceleration. Acceleration due to gravity is about 10, so we'll say it's 50 newtons down. How much force is he exerting on it? Well, 50 newtons up to keep it at equilibrium. So if Manuel weighs 375 newtons and is holding the box, how much force is the floor exerting up on him? So we'll add that in. So 425 newtons. How much force does each of his legs exert? We can chop that in half to be 212.5 newtons. And I'll let you draw your own free body diagram. Number 8. Firefly strikes a windshield, makes a mess. This is Newton's third law in action. The firefly hit the bus, and the bus hit the firefly. Which of the forces is greater? They are the same. So it's a trick question. Many people are familiar with the fact that a rifle recoils when fired. The recoil is the result of an action-reaction force pair. A gunpowder explosion creates hot gases, which expand outwards and allow the rifle to push forward on the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards upon the rifle. The acceleration of the recoiling rifle is, well, it's going to be smaller than the acceleration of the bullet. Because again, remember, force equals mass times acceleration. Third law guarantees that the force is going to be the same, but the gun has a much larger mass, therefore it will have a lower acceleration to compensate and keep that force the same. All right, that's that for this lecture video. Have a good rest of your day.